A bit about dynamo simulations, how they're done, and what some of the results coming out of these things. I thought I'd just start by reminding you, we've had most of this already from Karl-Heinz from Kandu, but the question that's quite often put to me in view of the sort of dynamo simulation work that I've done is what took you so long, and so I just want to point out what the difficulties are, and the difficulties are essentially that full dynamo simulations essentially have to be fully three-dimensional, and they also, as we'll see, they have to be run for a very long time, so that means that they are computationally demanding. Sort of simplifying things like having a dynamo, which could be with just planar flow to get a sort of two-dimensional flow driving a dynamo. That unfortunately doesn't work because there's an anti-dynamo theorem which tells you that if you've got a planar flow of that form, then you won't get any dynamo coming out of it. No restriction is placed on whether the field is 2D or not in that theorem, but nevertheless that is sufficient to make sure you don't get a dynamo. We've already mentioned Cowling's theorem that axisymmetric magnetic fields vanishing in infinity cannot be maintained by dynamo action. So if your object is to solve the equations from first principles, then it's no use looking for axisymmetric magnetic fields. If you want to do an axisymmetric calculation, you essentially have to rely on mean field theory, and then of course you have to put in alpha effects and beta effects, and these are to some extent actually unknown. So what I'm going to be talking about is not here mean field theory. I'm talking now about actually trying to solve the full equations numerically from initial considerations. And similarly, another simplifying thing, a purely toroidal flow might put that in with hope that would produce a dynamo, but unfortunately that can't work either. So that dynamos have kind of got to have radial motion. Okay, so basically in the Earth's core, as we'll see, the flow is clearly fully three-dimensional, and rotating convection leads to strongly non-axisymmetric 3D flows, and so simulations are inevitably going to be computationally demanding. It's not the sort of thing you can just sort of spend a Saturday afternoon writing a dynamo code hoping that you're going to get some results out by Sunday morning. It requires clusters of processors for serious study, so all the calculations that I'm going to be describing were not done on single processor machines, they were all done on much, much larger machines than that. It's not true that you can't do anything close to critical. There is one case where you can do stuff post-critical and use desktop machines, but it's very much the exception rather than the rule. So basically that means you're into parallel programming land. Nearly all the codes that I've been associated with have been written in MPI, message passing interface version of that system. Okay, so let's just go through the basis of the model. All the models I'm going to be talking about are essentially spherical geometry models. So they're basically all connected with the picture I was describing of the Earth's inner core. So this is the core mantle boundary here, this is the fluid outer core in here, and that's the solid inner core in there. And the radius ratio for the Earth is about 0.35, and nearly all the codes have actually used 0.35 exactly. So the inner core boundary is R in dimensionless units of 7 over 13, which works out of that, and R is 20 over 13, so the unit distance is the distance between the inner core boundary and the outer core boundary. Now we're going to be using spherical polar coordinates and cylindrical polar coordinates. Because of the rotation dominance, it's often useful to think in terms of the z direction, that's the direction perpendicular to the rotation axis, and then I'm going to call S the perpendicular distance, cylindrical distance coordinate in cylindrical polar coordinates, and when I'm talking about spherical polar coordinates, I'll use r theta phi. So two coordinate systems, r theta phi in spherical polars and s phi z in cylindrical polars. And as we'll see, this imaginary cylinder, which passes round the inner core, called the tangent cylinder, that's not a physical thing, it's just an imaginary cylinder there, but it's a very useful concept because a lot of the behaviour inside the tangent cylinder and outside the tangent cylinder is rather different. So I shall refer to the tangent cylinder quite a lot throughout this talk. It's helpful to bear that in mind. Okay, so we usually formulate these equations in dimensionless form in order to limit the number of parameters that we're actually dealing with. It turns out we're going to have quite a lot of dimensionless parameters, and the idea of writing it in dimensionless form is to actually minimize the number of parameters that you actually have in the system. So we're going to use the magnetic diffusion time, that's d squared over eta, where eta is the diffusivity as the unit of time. And then the unit of velocity is going to be naturally eta over d. So that means that when I quote a dimensionless velocity, that can be thought of directly as a magnetic Reynolds number, and that's the advantage of this particular scale. So when you see a number, a dimensionless number attached to a velocity, you can immediately relate it in your mind to the magnetic Reynolds number of the flow. As we mentioned yesterday, a natural unit of the magnetic field is this quantity here, and that's the quantity which is usually used in dynamo models. So that's the magnetic field, and that comes out to be about 14 Gauss, which is about 1.4 times 10 to the 9, 1.4 millitesla. Okay, so that's the unit. So we're expecting to see fields of roughly order of magnitude 1 in the dimensionless units because of that choice. And here we've got the dimensionless Boussinesq equation of motion. Now, most of the other talks have been concentrating on the induction equation. So this is, perhaps we haven't discussed this as much yet. This is the Boussinesq equation of motion here. So there's the inertial term, Coriolis term, pressure, Lorentz force here, and viscous force. And here are the buoyancy forces. And following the discussion yesterday, we have two buoyancy forces here. The temperature can drive it through the coefficient of expansion, so that alpha T can give you buoyancy, and the buoyancy force multiplied by rho G. And also light material can exist, so that's a compositional part of the compositional component of the buoyancy, and that represents, psi represents the mass fraction of light material. And in the core, we believe we've basically got a mixture of sulfur and oxygen, which is the light material, together, of course, with the iron, which is the heavy material. So the mass fraction of the light material is that psi, which is denoted there. To be more precise, that psi is actually the departure of the compositional variable from its basic state, which is assumed to be a well-mixed state. Departure of psi from the mean value within it. Now, you can convert that dimensional equation into dimensionless numbers, and at this stage we get these dimensionless parameters, Rayleigh number, Prandtl numbers, and Ekman numbers turning up. In order to get this, we've also had to make a unit of temperature assumption. So the unit of temperature is delta T, and that's the superadiabatic temperature difference across the core. And as I mentioned last time, convection is driven by very small departures from the adiabatic state. So a typical numerical value of delta T would be something like 10 to the minus 3 degrees K, which is only 1,000th of a degree. It's a tiny, tiny variation in temperature. And that is the sort of temperature variation which provides a sufficient buoyancy force to balance the other terms in those equations. So that is what we believe the actual superadiabatic temperature difference has that sort of magnitude. And the unit of psi naturally is to make it convenient. We take alpha delta T as that, and that again is absolutely tiny. We're talking about fluctuations of the order of only 10 to the minus 1 part and 10 to the minus 9 in density difference. It's quite sufficient to drive the convective flows that we see measured from the westward drift and the secular variation that I talked about last time. Okay, so now these dimensionless parameters. The first one is the Ekman number, which measures the ratio of the viscosity mu to the rotation rate omega. And then you need a d squared, where d is the distance between the inner core boundary and core mantle boundary to make it a dimensionless parameter. And because the distances are quite large in the core, the rotation is quite fast, and the viscosity is very, very small, this Ekman number turns out to be extremely small. The number in brackets is the true value. That's if you put in the molecular values of the viscosity and the correct values of omega and d, you get 10 to the minus 15 for the Ekman number. 3 times 10 to the minus 9 is the value that you might expect if you enhance the viscosity by a turbulent quantity. So this is based on a sort of turbulent diffusivity, and the idea of the turbulent diffusivity is we're going to take all the diffusivities to be order 1, as there. Now that's because that's really all you can do in the dynamo models. We like to take the proper molecular diffusivities and use these numbers in brackets, but that is just not numerically possible. So what we're actually trying to do is to enhance these diffusivities, well in particular enhance mu and kappa. It's not actually necessary to enhance eta. We take eta to be the correct value. That's the dimension of the value of about 2 meters squared per second. And so we have to enhance mu and kappa. And what we're trying to do, as best we can, we're trying to reduce the magnetic Prandtl number, and I'll show you towards the end of the talk a few examples where we've got sort of huge computational costs. We've got the magnetic Prandtl number down to about 0.1. So we can get something slightly less than 1, but we're miles off 10 to the minus 5, which is the correct value, or 2 times 10 to the minus 6, which is the correct value in the core. There's really no prospect of getting anywhere near that in the foreseeable future. Okay, so I've got Ekman number. So as I said, it's always going to be much bigger than the real Ekman number in the core, and indeed the computational Ekman number will be even bigger than that. As I said, it's really hard to get down much below 10 to the minus 6. Most runs, most computations are done in the sort of 10 to the minus 4 area. Some people have got down to sort of close to 10 to the minus 7, mainly because they sort of define their Ekman number with a few wave numbers different. Nevertheless, 10 to the minus 7 sort of represents the best possible current technology. No, it's possible. Then if you work out as a modified Rayleigh number, because this delta t is so small, this thing doesn't turn out to be so huge. I mean, it really is huge in reality because this is 10 to the 9. But within the framework of this turbulent diffusivity, we're going to be using a consistent value as of the order of 10 to the 3. And this is a modified Rayleigh number with omega on the bottom. If you want to convert to the sort of the Rayleigh number in Chandrasekhar's book, for example, then there's a factor of E difference, so that Chandrasekhar's Rayleigh number would be bigger than this by a factor of whatever. Okay, so I think that more or less copes with the dimension. Oh, perhaps I didn't mention, I ought to mention a bit more about, remember the magnetic Prandtl number is mu over eta, that's the viscosity divided by the magnetic diffusivity. And the real Prandtl, the ordinary Prandtl, fluid Prandtl number is mu divided by kappa, where kappa is the thermal diffusivity. And those are all dimensionless quantities. Okay, just about how would I get that estimate of the Rayleigh number? Because, it's just worth going through this. I think because we're taking PR and PM to be order 1, I've set those to be 1. G, the dimensional value is about 10 meters per second squared in the core. Alpha, the coefficient of thermal expansion, is about 10 to the minus 5. Delta T, the temperature difference I've taken as 10 to the minus 3. That's across the layer, so that's the super adiabatic temperature gradient. Remember, that's 6 orders of magnitude smaller than the full temperature gradient. The actual adiabatic temperature gradient is 1,000 degrees K. But the super adiabatic part of that is only a tiny fraction, about 10 to the minus 6 of that, so that's 10 to the minus 3 there. And D is 2 times 10 to the 6 meters, that's the distance, 2,000 kilometers between the inner and outer core boundary. The omega is 7 times 10 to the minus 5, and eta is about 2, and you put that together and you get that number of 10 to the 3. So that's where that number actually comes from. It's important to remember that it's got this very small delta T in it. You sometimes see some of the earlier papers sort of confuse the issue a bit by putting the full temperature difference across the core, but that's quite wrong. It's only the super adiabatic temperature difference which drives the convection.
Great.
Yeah.
But then in this case, this means that how we can be sure that the super adiabatic gradient is well known? Can it be wrong by order of magnitude, say?
I don't think it can be really wrong. Well, it could be wrong by a factor of 10. I mean, because, as I said, most of these, the kappas and so on and alphas, because of the very high pressure, we don't really know the physical constants that accurately. So it could easily be wrong by a factor of 2. Yeah. I don't think it could be wrong by orders of magnitude, because apart from anything else, you can estimate it directly, because if the convection is driving the whole system, yeah, then the buoyancy forces have got to be in balance with the Coriolis forces and pressure gradient forces, and we know what the Coriolis forces are in order of magnitude because we observe the secular variation, which gives us an estimate for U. So we have estimates for that. That's where this delta T value actually comes from. That's the crude way of actually estimating it, is to put those in balance. And in the simulations, as we'll see later, I'll actually show you some pictures of how that force balance actually works out in the simulations, and you'll see that the buoyancy force has to be comparable to the other forces, and you get sensible results. So here we've got the induction equation, which has been talked about before. Here we've got the temperature equation. So we could have heat sources in, if we want, in the temperature equation. And here we have the composition equation. There's one extra dimensionless parameter which has come in here, which is the ratio, the parameter number, compositional parameter number ratio of the viscous diffusion viscosity, kinematic viscosity divided by the compositional diffusion coefficient. Compositional diffusion coefficients are always extremely small, so PC would actually be somewhat bigger than 1 on molecular values. But again, it's when you simulate things, it's always taken as sort of 1 or close to 1 in the simulations. So those are the equations, and we can have source terms here and there if we want. Yeah, okay, so these are the internal heating sources and compositional sources, if any. What one might call the standard model, which isn't actually necessarily the one which is closest to the real physics of the core, but is the standard model in the sense it's nice and simple, it's computationally clean, and a lot of work has been done on it. So it's the one which we know most about, and it's the sort of reference point model, I would say, from which you sort of start thinking about, and then when you want to put special effects on, you sort of think in terms of the deviation from what I call the standard model. And the standard model is to actually ignore the compositional effects and have no internal heating, so that in a non-convecting state, the superadiabatic core is just given by the heat flux coming in from the bottom and going out of the top. And if you've got no heat sources, then you would have just the simple result of what comes in at the bottom, and heat flux coming in at the bottom is got to be the same as the heat flux leaving at the top in a steady state. So that's a nice, simple, clean model. It's sometimes called the differential heating model, as to oppose to the internal heating model, because it's driven by the difference in temperature and the difference in flux, the flux coming in from the bottom rather than any internal heating. So that's the simplest model, and that's the basic state that you would get for the superadiabatic particle temperature gradient. Just has this 1 square constant. Okay, so secular cooling, as I mentioned before, can be thought of as equivalent to uniform heating, and that has also been studied. The uniform heating case has been studied by Fritz Busser and other workers. It's not a very good model, really, of the real core, because more heat is carried down conduction down the adiabatic gradient as R increases. So actually a better model would really be to have cooling rather than heating. because heat is really being transferred from the convective process into the conductive process as you go up towards the core. So in effect, there's actually less and less convective heat flux as you go up, because more and more is taken out by adiabatic conduction down the adiabat. But you can see that the actual, when you get to detailed models, that it starts to get complicated, and you get different results depending on what actually particular details of your model. Well, there are quite a lot of decisions which have to be made at the beginning. So one of them is to whether you use stress-free or no-slip boundary conditions, and it does make a difference. Now, the natural thing to do is to use no-slip conditions. After all, the mantle is a solid boundary there, and the inner core is a solid frozen lump of solid iron, so of course physically you do have no-slip conditions. Some people have argued that it's better to take stress-free boundary conditions, and I've got some sympathy with that. The argument goes like this. The argument is that yes, you really ought to have no-slip boundary conditions, but your Ekman number, of course, is much, much bigger than it actually is. So if you put no-slip boundary conditions, the friction, the boundary friction, due to the Ekman layers that occur, is actually going to be much, much bigger in the models than it really is in the solid Earth. So it might be a better model to actually take stress-free boundary conditions and assume you've got no viscous Ekman boundary layer there at all, rather than putting in what is inevitably an artificially somewhat enhanced Ekman layer because of the fact that our Ekman numbers are much too big. So you can see the advantages and disadvantages of both ideas. I mean, the no-slip is sort of physically correct, but the stress-free might be a better model when you take into account the fact that our Ekman numbers are inevitably much too large, even though they're down to 10 to the minus 5, 10 to the minus 6, they're still much too large compared with the Earth's case. So, I think the best thing to do is look at both and to do studies on both and see what the difference is, and then try and make some kind of judgment about which one is most appropriate in different physical circumstances. I just put this one in the thermal boundary conditions because this is actually what the thermal boundary conditions should be. Nobody ever actually uses these boundary conditions in what you might call the classical situation. The simplest is to take constant temperature boundary conditions, and that's nearly always what's actually done in the numerical models. That's what we might call the standard model. But I'll just point out that in fact, if you go through the physics of the situation, you should really be taking into account the fact that as downward plumes impinge on the inner core boundary, they will actually melt locally the surface there, and that will release latent heat. So the flux would not be constant there. It would actually be affected by this parameter L, and write this in dimensionless terms. And when you actually work it out, you find that L is some number of 1. So that's really what the thermal boundary conditions, in a sense, ought to be from the physics. But as I said, in order to keep things simple, people have mostly gone for these boundary conditions here, which is just to set the temperature as 1 on the ICB and the temperature as 0 on the COB, which is the simplest possible sort of Rayleigh-Baynard type boundary condition which you can actually have. As I said, this, when you work out that dimensionless parameter, somewhat remarkably, when you end up with one of these calculations where you're putting loads of numbers of sort of 10 to the 8 and 10 to the minus 7 and so on all over the place, and rather miraculously the number comes out to be almost 1. So it's quite a surprise, but that's actually what actually happened. So it is a parameter review. So it really ought to be taken into account. And on the core mantle boundary, really a better model than the one we're actually adopting would be to take some kind of fixed heat flux corresponding to the fact that the mantle convection actually determines what the heat flux that can be taken out of the outer core is, and then you would really have some kind of fixed, that would really be fixed, so that it's really the flux which is fixed. I should say, I say that everybody does that. That's not quite true. I mean, there have been some recent papers actually where these kind of boundary conditions are starting to be used in dynamo models, and it does make a bit of a difference. I mean, not huge differences, but it does make a significant difference, a noticeable difference to the kinds of solutions that you get out. So I think that's one of the directions we're going to be going in. I think up to now there's been a tendency just to fix on sort of the standard model. One of the new directions that dynamo theory is going in is to try and explore these and to try and turn that sort of standard mathematical type idealized model into something more realistic in order to explore different physical assumptions. So yeah, and now there's also magnetic boundary conditions which have to be chosen. The most commonly used, I would say, are to match it on the potential field outside the core. That's completely standard, everybody does that. At the inner core boundary, there are two choices. The simplest is to assume you've got another insulating layer there, which is, as I said, simple but incorrect, because the actual conductivity of the inner core is comparable to that of the outer core. So what you should really be doing is matching the field across the inner core and solving the magnetic diffusion equation in the inner core. Of course, it's much simpler there because you don't have the curl U cross B term, you just have diffusion inside the core. In fact, I say this is simple. In fact, it's almost as simple numerically to impose this one here. So in a lot of the simulations show you that has actually been done. Okay. Oh yes. So another current hot topic in this subject is the issue of homogeneous versus heterogeneous core mantle boundary conditions. As I said, in the standard model, we assume homogeneous boundaries, so they're independent of the latitude theta and phi, the asymptotic coordinate. I must apologise that sometimes I use theta for the angle, the spherical polar coordinate of co-latitude. Sometimes it will appear as the temperature fluctuation. We'll just have to keep alert for that possible confusion. Okay, now heterogeneous boundary conditions are of interest because if you actually look at what's happening in the mantle, it appears really quite inhomogeneous. There are various parts of the mantle where large amounts of heat seem to be coming up from the bottom. There are cool places where slabs have descended from, continental slabs have descended, and they seem to go right down almost down to the bottom of the core mantle boundary. So at the bottom of the core mantle boundary is a pretty heterogeneous place. It varies quite a bit with position. In a way which we think we have some idea about. There's seismic measures can actually tell you roughly what the temperature differences are, temperatures are down near the core mantle boundary. And by looking at the variations in that, we get some idea of the places where there are hot spots at the bottom of the core mantle boundary. So it's possible to come up with some plausible model of what the heat flux distribution actually at the core mantle boundary is, and then you can stick that into the dynamo models and see what that does to the flow inside. And of course it changes things quite a bit because of course it means there's no static state. If you've got a heterogeneous boundary condition, then there is never a static state. There are always flows driven at whatever the Rayleigh number is. And initially, what tends to happen at sort of fairly low Rayleigh numbers, the flow pattern is controlled by what happens by what you put in at the heterogeneous boundary up here. And then as you increase the Rayleigh number, so the internal dynamics tends to take over and the effects become sort of muted somewhat. So it's a matter of parameter dependence. It's an interesting line of business, and again, it's something which is where there's been quite a lot of papers in the literature just recently.
Just to confirm it, so this core mantle boundary condition about temperature is not just directly inferred from the temperature measurements on the surface. It's just indeed measurements inside, right?
It's measurements inside, that's right. It's done from looking at the seismic velocity. There's what sometimes also high velocity zones, they call them, where the waves are moving slightly faster and is believed to be due to a slight temperature difference. I have to say, I mean, it's slightly controversial because some people attribute that difference to composition differences at the core. It's sometimes quite difficult to sort out. But the location of these places actually corresponds to, the seismic tomography gives you a definite pattern. Basically, the most popular pattern is basically it's a sort of P2 type mode. So it's a sort of ETI-5 with M equals 2 seems to fit the data, and that is often a P2 type spherical harmonic is often used in simple models of tomographic. Yeah.
How do you know that the seismic information is telling you about the boundary condition of the core, and not what the internal conditions in the mantle?
You don't get this from just looking at one earthquake data. Each individual earthquake essentially gives you an integrated version of the path along which it's travelled. Yes? But by looking at loads and loads of different paths, you can locate what's happening in the individual regions. You can essentially deconstruct the kernel, if you can imagine. So on each individual wave, the time it takes to go through, bounce, possibly back off the CMB, bounce back to the surface, that can be known. And then you work out from a different one, which has taken a different path. And so from looking at all this data, you can then work out at what level in the core velocities are. And that's how this has actually come about.
Is that happening on the timescale that you expect the mantle to be changing?
No, I mean, mantle changes are very, very slow indeed. I mean, millions of years are mantle. So basically what we're seeing is a snapshot. All this data is sampling essentially a snapshot. So nobody believes that the core is changing, the mantle is changing on that timescale. So basically, whatever it is, it's there. And so we're trying to measure it and trying to infer those details. This comes back actually to this very long time scale, comes back to the issue of the supercrons, because I mentioned that you've got a magnetic field can have one sign for 60 million years, you can have no reversals. So one popular idea about why that might be so is that time is actually controlled by mantle convection. That is to say that the core mantle heat flux got into a configuration which didn't favour reversals, which basically stopped reversals during the Cretaceous supercron. And now the mantle convection has moved around sort of 60 million, 100 million years later. It's moved around, and now we've got a core mantle boundary heat flux which is favouring rapid reversals. So that's quite a nice idea, because it sort of explains how the core time scale, which seems to be thousands of years, can nevertheless be related to a much, much longer supercron time scale of many millions of years. So that's an interesting point. So as I say, so there's a lot of interest in that, and of course then you might hope to be able to relate the observed sort of P2 type tomographic coupling to the kinds of magnetic fields you're actually seeing at the core mantle boundary. For example, those rather long-lived flux patches over Siberia and Canada, well, maybe they're there essentially because of the way the mantle heat flux at the core mantle boundary is actually currently in place. Okay. Right. So we've got these dynamo simulations and they're coming out, but then there's a question of how do you actually interpret what's actually coming out of these models? How do we compare the outputs with observations? If we were running with Earth-like parameters, there would be no problem. I mean, the outputs should be agreed with the observations. But because the viscosity and the thermal diffusivity are very small in a core, much larger in the simulation, we can't resolve that small turbulence. So what we've got to do is basically try to estimate what the effect of enhancing and reducing the thermal diffusivity is. In other words, essentially try and develop what are called scaling laws to see how the asymptotic limits are actually approached. And that's another very active area of research at the moment. So rather than just doing a run at a fixed value of Ekman number or fixed value of Prandtl number, what we're doing is varying those Ekman numbers and Prandtl numbers and trying to see what the asymptotic behaviour as these numbers actually become small is. And that gives you a better idea of the tendencies, the directions in which these models are going when they're approaching the Earth-like limit than actually doing any one particular simulation actually tells us. So that's basically, we'll never get it, of course, right down, but hopefully we'll be able to tell whether we're really actually approaching an asymptotic limit of small e with small Prandtl number, or whether we're not. It's still quite a long way off that, of course, but progress is being made. Now, there's another problem which has had sort of less headline coverage than the standard problem of the low, the much enhanced diffusivities. There's yet another problem, which is that even if you take mu and eta and kappa all the same, with sort of turbulent values of about 2 meters per second, square per second, then the Ekman number turns out about 3 times 10 to the minus 9, as I mentioned before, whereas the smallest e's you can get are in the region of 10 to the minus 6, so perhaps down to 10 to the minus 7 by really, really pushing it. But it's still quite a long way off that. So that actually does create a bit of a problem, because it means that the Rossby number is actually larger in simulations than the Earth's core, because in effect what we're doing here is we're running simulations not only with an enhanced diffusivity, we're also artificially reducing the rotation rate. So that the rotation rate in the models isn't really a day, it's really something like 100 days, or maybe several hundred days. And that has a sort of a slightly nasty effect, because it tends to mean that in the models the Rossby number is actually larger in the simulations than it is in the core. So whereas we like to be in a regime where the Rossby number is very, very small, because it really is very, very small, it's not nearly as small in the simulations as we'd really like it to be. So that's another thing you have to bear in mind when you look at dynamo model results. And that one is something which has been not really, I think, brought out quite as much as it should be, because this tends to make inertia much more important in simulations than it should be in real dynamos. Now, inertia produces lots of new interesting physical effects, and so people, of course, have run models with lots of inertia in them because they then get lots of new interesting results. And, of course, there may be planets where those results are relevant. There may be stars, there may be planets. So I'm not saying this isn't a worthwhile exercise, but I am saying that it probably doesn't actually apply to the Earth's core, because in the Earth's core the inertia is actually a lot smaller than it is in the simulations, because the Rossby number is actually a lot smaller, and that's introduced basically for inevitable numerical reasons rather than any physical reasons. There is actually another way around, which I personally quite like, which is actually to not just to increase the diffusivity mu up to the molecular value of eta, but actually to push it beyond that. And then you end up with larger Prandtl numbers, which people don't like because they say, well, the real Prandtl numbers are smaller. But I'd argue that since we've enhanced the diffusivities anyway, that's perhaps not such a problem. And if you do that, then you can increase omega so that at least you can then get the Rossby number correct, which in a sense I think is a better thing to do, because you get the balance of terms in the equation of motion are more accurately represented. Okay, so that's enough about the sort of the basic philosophy and what we're doing in dynamo models. Here's some results. This is the simplest one. This can be done on a laptop if you want to do it. If you've got a program that works, you can actually get this result out in a sort of day, I guess, from computing on the average laptop. The Ekman number for this benchmark dynamo, which the benchmark dynamo was organised by Uli Christensen in 2001, and everybody who had dynamo codes at that time spherical dynamo codes got involved, and we all ran these codes for this particular case to see whether we were all getting the same answers, and actually we all did. So the Ekman number is 1093, which is a very modest Ekman number. It's not really very small at all compared to 10 to the -6s what people are getting to nowadays. Ramp number 1, PM5, because that makes dynamo action simpler, nicer at these comparatively higher E, and Rayleigh number, a modest Rayleigh number of 100, and no internal heating, no slip boundaries, so this is the sort of standard case. And in a sense, this is why the standard case, or you might say, standard model has sort of come into existence because of this benchmark. And the configuration you get is nice and simple. You get an m=4 configuration, and only harmonics that are multiples of 4 are present. So it is non-linear, of course, so you get 4 and 8 and 12 and so on, but 1, 2, and 3, and those sort of things are all missing. And you get lobes of magnetic field generated, and the whole thing drifts westward in a steady rate. So it's actually a steady solution in a drifting frame, which is good for comparing things like the energy and magnetic energy and kinetic energy. Okay, and the radial velocity already begins to show a columnar structure, even though E is not all that small. There's nevertheless evidence of a columnar structure developing, and that's a sort of key point in these dynamo models, and I'll say more about that in a minute. Okay, so there's the westward drift in the benchmark dynamo, and that turns out to be about 3 times nu over d squared in dimensional units. So then there's the question, as I said, how do we estimate nu? And if you do the sort of natural thing, which is to work out in terms of use the magnetic Prandtl number that you've used in the simulation, and to take eta with its correct value, that gives you something which a frequency which is not unreasonable. It's a little slow compared to the real thing. Then a Rayleigh number is quite slow, so you sort of expect to get an answer which is quite. The Rayleigh number is quite small, so you expect to get something a bit slower than the real thing. So that gets you an answer which is not unreasonable for the westward drift. But if you try to use the true value of omega, then you get an absurdly large westward drift. And this is connected with this Rossby number problem that I mentioned before. It's just, you just cannot interpret the benchmark dynamo in terms of the correct omega. You've got to use the slow rotation in order to get the westward drift correct and get it into agreement with that. So again, you need scaling laws to tell you how to interpret these calculations which are being done, inevitably being done slightly wrong parameters. Okay, well, most of the codes that were described in the benchmark dynamo for these spherical dynamos are spectral methods. Now, I'm not saying that all dynamo codes are based on spectral methods. There are loads of dynamo codes out there which are non-spectral. But because the spectral methods have been around for quite a bit, and because they're sort of commonly used, and I also been involved in sort of developing them as sort of an interest, I thought I'd tell you a little bit about how they work. Okay, so the idea is that we start off by expanding all the fields in spherical harmonics, which is a sort of natural thing to do because the external fields are all expanding in spherical harmonics. So we use these YLMs, where these are the associated with Legendre functions, and these are the IL5, and that means that the coefficients we're going to be coming in front of these things are going to be complex, because we're interested in the real part, and we've got this complex representation here. And then we Schmidt normalize these things according to the sort of law, and it doesn't matter how you do that, so long as you're not consistent with everybody else. Then we do a toroidal colloidal expansion of the equation of the variables u and b. So we write u in that form and b in that form, which automatically reduces you down from 3 independent components down to 2, because that automatically gets div u equals 0 and div b equals 0. So one of the big advantages in a spectral method is you don't ever have to impose div u equals naught if div b equals naught. It's done right at the beginning by the nature of the expansion. If you use a finite difference code or a finite element code, you will need at each time step to correct, because after each time step you'll find that div b is not exactly 0 and div u is not exactly 0 in your computation, so you have to put in a correction at that point. Well, you actually avoid that with spectral methods, which is a nice feature of them. Then you insert these expansions into toroidal and colloidal parts, toroidal magnetic, colloidal magnetic, and you put those into the equations of motion, and you write the equations of motion in a particular way. That is to take the time-dependent term and the viscous term out on one side over here, and you put everything else over here in NU, which is sort of stands for non-linear because it's got non-linear terms in there. But in most of the methods nowadays, the Coriolis force, although it's linear in U, is actually now normally included in this right-hand side. When we first started doing that, we had the Coriolis over on this side, which made this more complicated operator over here. But it seems that as time has gone on, it seems that sticking it over on the right-hand side is actually a better idea. It doesn't really reduce the time step. I mean, the idea was that originally we thought it would reduce the time step, in practice it doesn't actually seem to do so. And again, with the nonlinear term, the induction equation, we write it in that form, and any composition equation that you use, whether it's for temperature or composition here, you write it in that form. And you have one of these or two of these. In most of the standard models, you just have one equation, like temperature property. Okay. So that's the form of the equations that we've got. And then how do we actually solve those equations? How do we get those vector equations down to scalar equations? When you take r hat, that's the unit vector in the r direction times the curl, and r hat dot, the induction equation. And in order to get rid of the pressure, you take the curl and the curl, the radial component. So those are the two equations that isolate the two scalars, and you end up with the induction equation in this form. So that is essentially a Poisson type equation here, time-dependent equation here, over with the right-hand side over here. Yeah, and so you've got to evaluate these right-hand sides. Okay, and for the velocity toroidal and colloidal components, you end up with something similar, except that for the colloidal bit, the operator is fourth order in space rather than second order in space. And that comes about because there are two boundary conditions to impose on the colloidal part. Whether you have stress-free or no slip, you're always going to have two conditions on the colloidal and one condition on the toroidal. And in the magnetic boundary condition, you have one condition there and one condition there at both boundaries. So this is inevitable because of the nature of the boundary conditions. You end up with a fourth order operator. And this way of splitting it up into a G, and that is essentially a Green's function type method, that seems to be quite a good way of doing it. Again, that's something that's sort of developed over time. People have tried all sorts of different approaches, of course, in doing this. And I'm just telling you sort of what the most popular choices are at present. Okay, so all those toroidal and colloidal coefficients are expanded into spherical harmonics, like so. So then the ALMs are functions of time, and they're functions of radius, and they're also complex numbers, of course. But because A has got to be real, that implies a reality condition, which is the complex conjugate of the minus m, got to be the same as the plus m of 1. So in a sense, you're only half as many coefficients as you might think you have. Okay, so these ALMs are now functions of r and t only. So that basically we can rewrite that operator in that form there. And the operator now only involves r and t on each LM, on each spherical harmonic. and at each time step you've got to get the nonlinear right-hand side of this thing here, so the nonlinear right-hand sides have got to be evaluated and decomposed into spherical harmonics, of course. So at each time step you have to get those nonlinear parts all separated out into a spherical harmonic expansion. Now there are choices to be made about what you do with the radial dependence. And there are two schools of thought. Some people are using finite differences. The code I'm actually using at Leeds does this with fairly high order finite differences. Gary Glatzmeyer's original code used Chebyshev polynomials, and that's what I was doing originally too. These are two alternative approaches. As you can imagine from the fact that we sort of changed from one to the other, not huge advantages either. Chebyshev methods are generally more accurate. Finite difference methods tend to be a bit easier to parallelize, so sort of swings and roundabouts of that. Typically, you can put all the measure points, all the variables at one measure point on one processor, so it makes it sort of nice and convenient for the parallelization, which is why we're doing it like that at the moment. So then the insulating boundary conditions, well, the boundary conditions come out really nice on the magnetic field because you've got to just match to an external potential, and that's very easy to do within the context of spherical harmonic expansions. And then there are no slip boundary conditions or stress-free boundary conditions. There's not a lot of difference from the point of view of complexity of these. As I mentioned, we're using this Green's function method, which I'll just describe in a little bit of detail because this may be unfamiliar to some of you. For example, for the no-slip case, what do we actually do? You actually solve this set of equations here, like that, with drPu0, that's the correct boundary condition, and this is not the correct boundary condition. You just solve directly with G equals 0 on both boundaries. So that's easy to do because that gives you a simple solution, but it's not the correct solution. But in order to get the correct solution, all you have to do is to add on essentially a combination of something which is pre-computed. So you add on multiples of P1 and P2, which are pre-computed solutions of that Green's function there. And then the required solution, which satisfies the correct boundary conditions, can be written as the one where we use the incorrect boundary condition, that's the G equals 0 boundary conditions, plus these two bits here, where A and B are arbitrary numbers, multiplying the solutions P1 and P2. Then you put that back into the boundary condition equations. That's the influence matrix here, it's sometimes called. And then you solve for A and B, and then you've got the full solution that you really want. So that's quite a convenient way, and it seems to be robust and fairly accurate. So sort of a nice thing to do. So I definitely recommend somebody to use that rather than directly trying to solve a fourth order problem directly with the fourth order matrix, which is what we used to do. Currently we're using Crank-Nicholson, implicit Crank-Nicholson for the time stepping part of it, which is a sort of common, actually a subscript T, sorry. It's a half of the thing evaluated there, so that's implicit because this appears on the right-hand side. But this causes no difficulty because the del squared operator is very, very simple in spectral formulation. So you can't treat the nonlinear terms implicitly. That's off the menu because that would require solving a whole set of equations which would be vast and would take far too much computer time. So what we usually do is something like Adams-Bashforth, which is we estimate the current nonlinear step by looking at the current one and the previous one, and that gives you something which is second order accurate in space and in time. Okay, and how do we choose the time step? Well, in most of the codes at the moment we're using predict corrector methods, so that means that you find yt plus 1 in the normal way from using that. And then once you've got yt plus 1, you get a better estimate of the nonlinear term using the yt plus 1 you've just calculated, and then you do it all again at that time step using this improved value estimate for nt, and then you check whether the improved value is close to the original value, and if it is close to the original value, you deem that your time step is okay. If it's too close, if it's really, really close, then you can increase the time step in order to get you through the calculation faster. But if it's too far apart, you've got to reduce the time step at that stage. So the time step is controlled essentially dynamically in this way. So you don't need to decide what the time step is before you begin. It's chosen throughout as you go through the calculation. That turned out to be quite important because in these dynamo calculations, for reasons, I wouldn't say reasons you totally understand, there are certainly what you might call bad times and good times. And the bad times, the time step goes down, and the good times, the time step comes up, and if you chose the worst possible, smallest possible time step to cope with everything, you'd be wasting a lot of time during what you might call good times. So the workload of spectral methods, what is that? Well, basically, most of the work is in evaluating the nonlinear terms. All the differentiation is always done in spectral space. So when you've got these nonlinear terms with the derivatives in them, they also have products in them. And the way you evaluate everything is you do all the differentiation in the spectral space, where it's really accurate, because you've got exact formulas for differentiating associated Legendre functions that you'll all know things. Of course, differentiating exponentials is very easy. So you do all the differentiating in the spectral space. Once you've done that, you then convert everything to a grid. And the grid should have more points than the number of spectral things. The 3 halves rule is the one that's usually used. So you usually have sort of 3 halves as many points on the grid as you did spectral codes. You get everything evaluated on the grids, and then the products you actually multiply together on each individual product. So that u dot grad u, for example, will work out u, and you work out grad u, you multiply those together on the mesh. And when you've done all that and got it on the physical mesh, then you back transform to spectral space, so those nonlinear terms are all sitting there spectrally decomposed. So you can see that what you're doing quite a lot of is converting between spectral space and physical space. That's the space on which everything is multiplied together. And that is the slowest part of the calculation. That's the thing which sort of limits it. All the differentiation is almost instantaneous, because they're all sort of standard formulas. They're just multiplying numbers together, or multiplying the spectral coefficients by numbers. So that's very, very simple. The problem is always actually converting between the physical space and the spectral space.
And the time stepping and data storage is in spectral space mostly?
Yes, yeah, that's right. Yes, yeah, that's right. Yeah, we keep the coefficient in spectral space. So that's what we actually store. So that when we want to reconstruct pictures, we start with the spectral space and then convert those onto some kind of physical space. And the advantage of that is you can either have a fairly low resolution look if you want, or you can, if you want to produce something for publication purposes, you do it at full resolution. So that's sort of quite convenient. Now, in Phi, the business of converting between spectral and physical space is no problem, because there's the fast Fourier transform, because of the special properties of e to the IM Phi, which enables you to do that very, very fast. Essentially, it goes like n log n, where n is the number of points in each dimension. Unfortunately, there's no real useful fast Legendre transform. There are fast Legendre transforms. This statement is in danger of becoming out of date, actually, because as time has gone on, of course, we're doing bigger and bigger models, and we're really getting to the point where the Driscoll-Healy algorithm, which is actually a fast Legendre transformation, it's got a lot of overheads. We're getting to the point now when we should really be using that, actually. I mean, it's a big coding job, and I'm sure somebody will do it. Not too distant future, but it's one of the problems that's sitting out there, which hasn't actually been done yet. So currently, the codes are running, and for a conversion in each theta direction, these n theta squared operations. And this means, of course, that the periodic box is significantly faster than spherical geometry. So that even with Driscoll-Healy, this would still be true, actually. It's always going to be the case that you'll get a lower Ekman number if you're in a periodic box than you will if you're in spherical geometry, because of the difficulty of the Legendre transform. Okay, so I hope that's given you some idea of how we actually do these things. Normally when people give talks, they never talk about that details of how their codes work at all. So, and of course, it's also probably true that you can drive a car perfectly well without knowing how the engine works. But this is, it's not really like that. You really do need to understand a bit about what's actually going on behind the codes before you actually start using them. Otherwise, you can go horribly wrong and think you can discover new things when you haven't really at all. Just using the code properly. Okay, so there are two sets of codes out there. There are finite difference codes out there, of course, which pencil code is one of the best established. There are finite volume codes sitting out there. K.K. Zhang has a finite volume spectral, well, it's really a finite element method. The Eastern Europeans, Maxim Reshetniak has got a finite volume code, which Pavel Hader's also worked out. So there are a fair number of these codes sort of sitting out there. The advantages of these things are generally they're local, so they're easier to parallelize. Also, there's a possibility of using fully implicit methods with these things, which there isn't really with the spectral methods. They're just too involved for that. So those are two perhaps important advantages. The disadvantages is that you can't, that differentiating is much harder in these kind of things, so that you typically have to have a lot more variables floating around. The very neat formulation that you get from spectral methods is sort of missed. And the boundary conditions are typically more awkward, and the solutions are also typically somewhat less accurate. Again, if you're naive, problems often come up with a pole similarity problem. That one has been more or less avoided by the Japanese, the use of this yin-yang grid, which covers the thing, grid points covered in two sort of patches, one of which goes over the North Pole, one of which goes over the South Pole, and these are joined together in the equatorial region. So that can definitely be overcome, but nevertheless, they're complications. Okay. Results, well, I'll still say that probably the spectrum methods have the advantage at the moment. And it's possible that when the number of processes we can use get really, really large, then I think finite difference methods and the finite element methods will start to come into their own. It's very difficult to say because computer technology changes in all sorts of complicated ways. I mean, if you go back 5 years ago, I thought that spectral methods would be on their last legs by now. But then, of course, some smart guy worked out a faster way to do the interconnects in processors. That makes parallel spectral methods hugely more efficient again, because the big problem with the spectral method is this physical to spectral conversion, and that does require moving off onto the mesh. You've got to transpose matrices to do that. So basically, you have to have all-to-all operations. You have to distribute information from one processor to another processor, and if that was going to be a very, very slow operation, the spectral methods would be inappropriate. But then somebody invented a way of connecting things up faster, so it's hard to second guess where the computer technology results are going to take us. Okay, so let's have a look now at some results from these codes. So this is slightly smaller Ekman number than the benchmark dynamo, so it's sort of slightly moving to a slightly more realistic regime, but still miles off the true. And you've got a slightly higher Rayleigh number here on PR PM1. This is one that's been studied fairly well as well. So again, it's the standard model, no internal heating, just differential heating, no slip, fixed temperature, insulated boundaries. And the interesting thing about this is, straight out of the box, so to speak, we've obviously got a huge mean field. So there's no doubt that these rapidly rotating convective dynamos produce decent mean fields, really without having to struggle. I mean, this happens sort of almost naturally in the thing. And we see in this picture, it's quite interesting because there are sort of intense flux patches at high latitudes. Basically, those are just outside the tangent cylinder. The tangent cylinder pokes up over there. So those sort of correspond very nicely to those flux patches that we talked about in the real thing over Canada and Siberia, which actually turn out to be, again, just poking out above the tangent cylinder in the real thing. We've got a highly dipolar field. In fact, the problem here is not that we have, not that we're failing to get a mean field, we're getting too much mean field. This is actually too dipolar dominated. If you remember the picture I showed you last time from Andrew Jackson's thing, he has quite a lot of sort of reverse flux patches floating around here. This thing doesn't. This thing is actually more dipolar than the real thing. And certainly in the fourth lecture, I'll talk quite a bit about that. But I thought, yeah, I'm just going to try a little experiment here. I've got some videos, but I didn't put them into the presentation, so I'll just have to let's show that out. Let's have a look at this. Should be wonderful. That's BR, isn't it? Yes. So this is a little movie. It said BR, so presumably this is the BR one. Yeah, it is. Yes. So this is the movie of how this thing is actually operating. So you can see it's drifting, yeah, in a sort of irregular fashion, westwards, like so. These patches are drifting in, again, fairly westwards. So westward drift is what we want to see, but of course these are more uniform actually than the real thing. The Pacific Ocean hardly drifts westward at all, the Atlantic does, but this thing drifts more or less westward all the way. You can see these flux patches growing and decaying. When it goes to the white, that's because it went over the IDL limit. I'm sorry about that. And then you can see these. There are some reverse flux patches in these kind of models, but they tend to stick quite close to the equator. So that's the sort of time development of that. And if you work on the magnetic diffusion time scale, then the period of the westward drift sort of corresponds to what you expect. Let's just get rid of that one. I can see that the UR is here, isn't it? So this is the velocity, so this is the radial velocity. Of course, the radial velocity at the Corpuscle boundary is 0, so you have to go a little bit inside the Corpuscle boundary to see the patterns. So this is about 0.8 distance out. And here you can see the columnar structure becomes very clear. So we're getting convection rolls. When I talk about the theory, we'll understand why these convection rolls come in rapidly rotating convection. It's exactly what you'd expect. And here you can see these tall, thin columns moving around, and the smaller you make the Ekman number, the thinner these columns get. So there are lots of tall, thin columns moving around. These columns exist primarily outside the tangent cylinder. Inside the tangent cylinder, the convection is still in the form of columnar convection, but its form is slightly different. I think I'll just run that again, because that's worth having another look at, I think. You can also see in these kind of simulations but the thing is, these rolls are not steady, they come and go. I mean, if you look at each individual one, they develop, that one sort of just suddenly disappear. They tend to have quite a long lifetime, actually. They sort of come, they go, and they come and they go. So this is not, it's certainly nothing like delta correlated turbulence. Within the context of what Karl-Heinz was saying, the Struwell number will certainly be of the order of unity, if not even more, I think. And these things, certainly nothing like short sudden time calculations here. So there's quite a lot of long-term correlation in these kinds of pictures here.
So what is the color coding and what is...
Oh, sorry, the color coding, yes. Sorry, yeah. blue corresponds to it's the radial velocity we're seeing there. So blue is negative and red was positive. Yeah? So that means the red was fluid flowing out, yes, and blue is fluid flowing in. So that if you look, for example, there, that tells you that on this side here, there's fluid flowing out, yeah, and at this side, fluid flowing in. So what that corresponds to is a convection roll. It's essentially a columnar roll going round and round like that, yeah? And you see that these nearly always associated with blue and red sort of tend to come together like there and there.
So this is at the surface?
No, this is at 0.8. So if you so you've got the radius, you've got the inner core boundary radius, the core mantle boundary radius, and now you imagine a sphere 4/5 of the radius out from this one out to that one. Yeah. So it's not quite at the core mantle boundary where everything will be 0, of course. It's a bit inside that. Okay. So those blue and red sort of lines are essentially convective columns rotating around like that. And actually, the magnetic field is strong, where in the back BR picture you have those big black sort of blodges which are even going over the top of the colour spectrum there. Those tend to be at the top of these rolls. So where you've got a nice strong roll like that, then you get a nice strong flux patch up at the top, and they're all coherent signs, so that all the individual flux patches are all the same sign. They're all positive on the top and negative on the bottom, and so the whole thing adds together to give you the big axisymmetric dipole contribution. So that's how it's actually working.
There's a magnetic Reynolds number which you said was several.
Yeah, the magnetic Reynolds number is about 100 for these flows. Yes, that's the global magnetic Reynolds number, about 100. Of course, if you notice that these things, these columns, are quite thin, so that actually, if you look at the local magnetic Reynolds number, what the small non-axisymmetric columns are doing, that is nothing like as big as that. So that is actually probably not that large. So in other words, first order smoothing is probably actually operating in those individual columns. The individual columns will be turning out the mean dipole field, yeah, but not a huge amount. So you won't have the problem of the Parker twisting it around many times here, because the RM is relatively small in those columns. Then what Karl Heinz was mentioned as the first order smoothing approximation this morning, that is probably operating here, and that I think is why this whole thing is working so well to give you a nice dipole magnetic field. So the problem of decorrelation of individual fields from various edges is not really happening here, because the amount of twist here is not that large, and so the fields are just nicely being turned, as indeed in the classical Parker picture. So that's why it's all sort of hanging together rather nicely. But it's all a consequence of this. I mean, really, we do have two scales here. We have two scales because we have these two tall, thin columns, which is providing one length scale, and the much larger length scale of the whole top to bottom length scale, which is like the whole length scale of the core. So that's why the mean field picture is actually giving us quite a reasonable insight into this. And in lecture 4, I'll come back to that and talk. I mean, it's possible not just to it's possible to make useful predictions as well as some useful predictions here. As well. Okay, so that's that. Right, okay, so what happens if we go to lower Prandtl numbers? This is one at PR and PM is 2. The other parameters are the same, 10 to the minus 4. And you can see straight off that something has gone wrong. This is much less dipolar than the previous one. There's still sort of some red up here, but there's loads of blue up here as well. In a sense, we've moved too far from this in this picture. I mean, whereas the previous one was too dipolar and had not enough small disturbances. Now we've got loads of small disturbances all over, and this is not really sufficiently dipolar as an Earth model. So really, by moving the Prandtl number, we seem to have gone from one extreme to the other. What is actually happening here? Well, this type of dynamo is strongly affected by inertia, because the PR and the PM have gone down here. That has effectively meant that the Rossby number has risen, and so inertial effects are starting to come in. And when inertial effects start to come in, you start to lose those beautiful axisymmetric dynamos, dipolar dynamos, and things start to become really complicated. And a popular idea is that in some way the Earth is somewhat on the boundary between the dipolar, very low Rossby number regime and the inertial regime. And if you look at dynamo simulations long enough, this seems a very attractive idea. The problem with it is that, unfortunately, it just doesn't fit with the numbers. If the viscosity and the numbers we believe are there in the core, we should be in the totally axisymmetric regime. I'll come back to this one several times. So the main problem we're seeing at the moment is when we move towards Earth-like parameters, our dynamos are becoming very, very dipolar dominated, and the real thing sitting underneath our feet is not like that. So clearly there's more to go. That's no surprising. More to do. Okay, so, and this is the flow at lower Prandtl numbers, and you can sort of see that the columns are sort of beginning to break up here. There's more activity near the poles, and there's less obvious. There's still some columnar convection going on here, but it's much less evident. And this is part of the inertial business, because part of the reason for the columns, of course, is Taylor-Proudhon theorem, and Taylor-Proudhon theorem relies on low inertia. It applies to slow-moving flows. It applies to flows where mu.ground u is negligible, and that's no longer being the case. So it's no great surprise that we're beginning to see that. And we did some work on that, and we'll sort of come out just about okay. So these ones here are higher Prandtl numbers.
Yes,
yeah.
The one which was dominantly dipolar doesn't reverse ever?
No, never reverses. Exactly. So that's another reason why we don't like these very heavily dipolar dynamos, because the real thing reverses. Those never reverse. You could sit there for a lifetime, and I'm sure that would never reverse. No sign ever.
And you start these simulations with random initial seeds?
When I get to lecture 4, I'll talk about that. Yes, this one was not started from a random initial seed, actually. This one was started from the benchmark dynamo, in fact. And where you end up actually does depend on where you start. But that's quite a long story. In lecture 4, I'll talk quite a bit about that, because it's a very interesting story, I think. And it's one sort of just emerging sort of recently. But let's get back to this, which is slightly older work. So this is the mean magnetic field here. So that's the root mean square of magnetic energy density, basically, plotted as a function of diffusion time. Come back to the point that was being made in the previous seminars. It does take a very long time before these things really settle down, before you get these nice axisymmetric pictures. So we usually run these things for sort of typically at least the diffusion time, sometimes magnetic diffusion time, sometimes many more before we're certain that we've actually got the right asymptotic behaviour. And then it can be quite deceptive, because even when you're on things like that, you can suddenly find that these things are moving very slowly in one direction or the other. So it really is certainly the biggest mistake that everybody made at the beginning was to run their models for too short a time. Virtually everybody did that, because, I mean, you don't want to sit there all night, do you? Watching this thing grind away. So the temptation to cut it short is huge, but it is unfortunately a disastrous thing to do. So you really do have to run these things for a long time. So, as I said, well, we all made that mistake. But the difference here is this green one here is in the inertial regime, and it does show you, the point of this thing is it really does distinguish here between the low Prandtl numbers, which are definitely in a different regime, But once you get up about 0.5 or 1 or 5, you're then getting some kind of an asymptotic regime in which we believe u dot grad u is sort of disappearing from the equations of motion. So these are actually genuinely non-inertial solutions up there, and that seems to be a fairly well-defined limit, mathematical limit of these equations. So the magnetostrophic limit. And that's the flow also different, so that's the low Prandtl number, there's more messing around, there's more fluid flow. That's the magnetic Reynolds number, so that's the root mean square magnetic Reynolds number average over the whole thing. So that's what I said, it's just slightly less than 100 in these type of numbers. So there is a low Rossby number limit which is beginning to emerge, which is sort of interesting. And this is the, these are the force balances. So what we do here, I mean, it's a bit arbitrary in the sense that you have to choose a component of the force, but we've just chosen the radial component of the forces when they're vector forces. So we plot the modulus of J cross B at a particular radius. I think this is about halfway out, sort of in the middle of the fluid here. And what we do is, we look at the relative strength of these forces, and if it's dominated by one of them, you get it almost black, and if it's making hardly any contribution, we give you a white pixel there. And so what do we see here? We see that in these calculations here, the Lorentz force is quite comparable. Well, it's slightly smaller, but it's sort of, it's on the map compared to the Coriolis and the buoyancy forces. The pressure force we haven't actually included in this picture because that just takes up the slack, so to speak, so it's sort of physically slightly less interesting. So the buoyancy forces and the Coriolis forces are in balance. That comes back to your question at the beginning, which was how do we know about 10 to the minus 3? If you now put the numbers in order to get that kind of a balance, then that's the number you actually need. That's where that number comes in. So clearly, in the low Rossby number limit, the Lorentz force is playing an important role, which is somehow disappearing in the inertial regime. And here we've got, to finish it off, we've got the inertial forces, that's u dot grad u, where it's actually u cross omega, which is another way of writing it, are written out for those, and you can see that it really is inertial, that the inertia really is important down there. It's taken over the role of the Lorentz force, so that essentially what's happening is that the Lorentz forces are being replaced in the inertial regime by u dot grad u, and so things are going down the inertial route, and viscous dissipation is important in these things, whereas in these ones up here, the magnetic dissipation is more important. And the viscous forces are all pretty small anyway, everywhere actually, in all these models. That's because the Ekman numbers are really quite small. So, of course, they end up dissipating a lot because they're through the derivatives, but the actual magnitude of the forces are quite small. So this sort of reinforces what I was saying. What happens if you go down to 10 to the minus 6? So this is a very low Ekman number. It's Prandtl number 0.1, so we're pushing it here. So this is sort of much more like Earth-like parameters than the previous one. And what is actually happening? Well, we're getting even more dipolar than the previous one. So we're really getting these rock-solid dipoles here. And these, you can sort of see that the structure of the small-scale structures are becoming really quite small here. Field strength is a little weaker, but that's not really a problem because it's sort of not far off Earth-like values. So it's field similar structure, but it's even more dipolar than it was. And the fluid Reynolds number is now considerably higher. But the fact that the fluid Reynolds number is higher still doesn't alter the fact that you're still getting these columnar structures, and you're still getting this massive mean field, mean dipole field. Interesting. Here are the small E pictures. So this is sort of what I said. If you compare those with the larger E pictures, well, it depends a bit where you are in radius. This is halfway between the, that's 0.5. That was a bit misleading. That means it's actually halfway between the inner core boundary and the outer core boundary. This is 80% of the way out from the inner core boundary to the outer core boundary. And as you go further out, you can see the columns become thinner, but they're still much thinner than they were before, even in the interior. So the net effect of going down to lower E is always to make the columns thinner and thinner in these calculations. Ultimately, we believe that magnetic forces will stop that getting thinner and thinner and thinner, but it's very difficult to get there. I mean, at the moment, that's almost out of range of the numerics. I mean, we're beginning to see some effect of the magnetic field on the wave number to stop it getting smaller and smaller and smaller, but in these models, we're not really in that limit yet. So it's still another indication of there's still more physics out there that these models are not capturing, of course. Yeah, this is another one which has sort of interested me a bit. This is quite a recent picture. We've had this data around quite a long time, but I just sort of got around to actually looking at it. This sometimes happens, I'm afraid to say. This is the one with Prandtl number 0.1, so that one might expect the magnetic field to have larger scale structures than the velocity field. And indeed it does. If you look at that, you can see that although there are still columnar structures that are found in the magnetic field, they're much, much wider than the structures, corresponding structures in the velocity field. So you are beginning to see some kind of scale separation between the small scale velocity field and the somewhat larger scale magnetic field that one really expects at low magnetic Prandtl number. Of course, as you go to very low magnetic Prandtl number, you would expect to see tiny fluid structures because the dissipation is so small there, and much larger structures in the magnetic field because the diffusion is much greater there. Okay, well that seems to be a good place to stop. I think I'll stop there for this time. Okay, so is there any questions on any of that? Yes.
It's about compositional convection.
Yes.
It's treated largely as thermal convection, right?
That's right.
But thermal convection, you know, we all make these experiments with thermal convection every morning, putting water in the kettle, right? Are there experiments with compositional convection? Is this theory supported by experiment?
Oh yes, yes. There's the ammonium chloride experiment. Dave Loper has a wonderful ammonium chloride experiment. You take an ammonium chloride solution and you stick it in a sort of beaker and you stick it on dry ice, and that cools it right off the bottom, and then the ammonium chloride sort of comes out of solution and it sort of forms wonderful little plumes. The chimneys start to form, and then the ammonium chloride forms a sort of matrix at the bottom, and then what happens is you get sort of little chimneys coming out. So you get little sort of plumes, thin plumes of convecting material zooming up through those chimneys. And so, I mean, that may be sort of thing what's pattern that you've actually got in the core, but you can certainly see compositional convection stirring the fluid exactly along these lines. So, yeah, so the answer is yes, I mean, we do know that that's what happens. Although, as ever, when you get into the details, it's more complicated because the ammonium chloride forms this sort of matrix, and so there's a solid fluid interaction in the boundary layer, and that boundary layer is actually really rather important in controlling the pattern of convection, and that of course is not in these models at all, because in these models at all we just have a much simpler amount of convections. So generally speaking, I'd say that there's a lot of mileage probably in looking at different boundary conditions to get out different effects out of this, which has not really been done, partly because it's a lot of hard work.
Can I just ask on this? In astrophysics, there's a thing called Ledoux convection.
Yeah, so
is that actually the same thing?
The same
What
thing, yeah.
It's called
Ledoux convection. Basically, yes.
It results from the fact that the
molecular weight gradient.
It's a mu gradient. So if you have helium, if you burn stuff into helium in the outer shell, for example, the helium of course is heavier than the hydrogen.
Yeah.
And so
but in that case, of course, it's going to be sort of stabilising. So then the composition can be sort of stabilising, and the convection is then driving. So you can have situations either like this where they're both destabilising. You can have situations where one is stabilising and the other is unstabilising. The helium rain out in Saturn, of course, it comes the other way around. So that again is sort of a bit like the convection, but that's again destabilising. course, there's a whole host of interesting phenomena called double diffusive convection, which all rely on the fact that the diffusion coefficients are different, and again, all that is missing in these models because we're basically saying.
Maybe what I just said was actually not right. The thing was that the U gradient could stabilize the convection.
Yeah, that's right.
Even though the entropy gradient is still unstable.
That's right.
And I think that can actually lead to
yeah. Well, it can lead to oscillatory type
convection.
Oscillatory type of
Yeah.
convection.
Yeah.
That is correct.
That's
Maybe that kind of thing can happen in the core too. I mean, maybe regions where you actually have completely stable structure as well. That's something that's been suggested recently.
Can do.
Yeah, I was just wondering I'm still not clear, what sets the scale of this plumes which are coming out?
Well, in the simulations here, that is set by the rapidly rotating convection. Yeah. If you look at rapidly rotating convection, if you just do the linear theory of rapidly rotating convection, you find there are tall, thin columns, and the thickness of the columns is e to the 1/3. Okay, and so E is sort of quite small in these calculations, so e to the 1/3 is also quite small. So that is actually what's set in the scale of this calculation. And e to the 1/3 scaling seems to work pretty well in all the models. Basically, if you look at a model, if you make E 10 times smaller, then the columns are half the thickness. So it more or less seems to work fairly.
In this, how does it break up like this? In this picture, the velocity field seems to have broken up into.
Yeah, that's because we're at very low Prandtl number there. So we're looking there. So that very low magnetic Prandtl number, it becomes a bit more complicated than just a straight columnar type calculation. And that, as I said, that one seems to have broken up. There are still columnar structures within that. Actually, if you look, that's just an equatorial section. That's a section that. It's just slightly above the equation. It's a z equals 0.2, which means it's not quite up to the top of the inner core slice, just above the equation. Okay.
You said in the beginning that it's more realistic to employ stress-free boundary conditions.
Yeah, well, I mean, that's a point of view. I mean, yeah, that's a point of view.
How about the precision-driven dynamos or precision-driven flows? Do you think similar arguments apply there too? Or
well, it's more dangerous, I think, there, because the precession-driven dynamos, the boundary layers really play quite an important part, and they can be significantly damping. I mean, if you put stress-free boundary conditions in there, you're possibly living in a bit of a fool's paradise, because then you've eliminated this source of dissipation outside, which can actually damp the whole thing down. So, from a sort of tactical point of view, it would be rather dangerous to assume, I think, stress-free boundary conditions in those, because you get lots of nice dynamo action, and as soon as you put the no slip back, it will all go away. Whereas here, it's sort of the other way around, in a sense. We're trying to get rid of these dissipative layers because we think they're introducing artificial things that are not actually affecting the internal dynamics.
A few slides ago, you compared the forces in the
sure, yeah.
And the viscous forces at the outer boundary were pretty low. So is that you've got to be a bit careful there because they're not that low actually. The Ekman layer is very, very thin. That's let's see if we can see that. Yeah, you can hardly. It sort of gets a bit lost actually there. There is actually a very, very thin layer there, where if you look at it more carefully, it is actually significant in that very thin layer. So the Ekman layer is the order e to the 1/2 thickness, and so these are rather small Ekman numbers. E to the -½ is really very small. So this layer is very thin. So this is no slip.
So this is no slip. Yes, this is no slip. That calculation is done. That one was done for no slip. That's been on. Extremely less in Jones 2006. So, okay.
Yes, please.
So you use non-realistic parameters in your simulation to.
I have to, yes.
So the reason is, is to compress the time scales of different phenomena, right? So you can
No. The reason is that if you use the realistic parameters, yeah, you get loads and loads of small scale phenomena coming in. Yeah, you get a full cascade down to small scales, and you can't resolve that. So it's basically the resolution which is limiting us. Yeah, basically, you have a certain amount of resolution, and that means you can go down to a certain Ekman number and still capture everything correctly. Yeah? If you try to go at an Ekman number below your resolution limit, then you don't, your spectrum is not cut off properly. Yeah, I should have said this actually. In one of the tests of whether your spectral code is running correctly is to look at the spectrum. And what you've got to see is that near the end of the spectrum, you've got to see the modes dropping off exponentially. And that's what happens when the thing is properly resolved. Yeah? Now, that will happen, that happens in these runs, because those runs that I've shown you are all properly resolved. But if you try to go at an Ekman number below what your resolution will allow, then you won't get a proper cut-off to the spectrum. It'll just stop. In fact, it's worse than that. It not only does it stop, it starts to go back up again, and that means you've got total rubbish basically at that stage. So the problem is that what's limiting us is the scales we can capture in our models and the scales that appear at various Ekman numbers. And you can't go below the Ekman number at which those scales below your grid stuff is actually going. And that's basically what limits the Ekman number. And of course what limits the resolution is just the time. It's just a computational time. You can try to, gosh, we're running out sort of 256 in all directions, typically, that kind of thing. So actually, we usually do slightly less radial and slightly more fine, but basically it's sort of the order of 256 in each direction. And that takes a long time to run because you've got to run it for a whole diffusion time, basically. So you've got to run these things for a long time with high resolution. That's what's actually limiting you.
So in your scheme, do you have numerical constraints on the time? Because it's implicit.
The time step, yeah. The time step, well, the constraint comes from the predictor corrector. So,
yeah, right.
So the predictor corrector tells you whether your time step resolution, whether you're resolving things in time correctly. So that is actually set automatically by the code, and it will turn out to give you sort of values around 10 to the minus 5 or 10 to the minus 6 of the diffusion time. So to run a full diffusion time, you've got to take between 100,000 steps and 1 million time steps before you're fully resolved. So that's where you've got to go. And then so that means if you're taking a second a time step, well, you can do the sum. 10 to the 6 is a million time steps, and that's, well, 3 times 10 to the 7 seconds in a year, so it's a 30th of a year. So you're realising that you're not going to get things back in a hurry if you're in that kind of.
But you can still use fully implicit scheme.
Fully implicit? People have done. There's Stefan Stelmark and Uli Hansen adopted a fully implicit finite difference scheme, and we were running our codes. I'll report to you the sort of conversations we used to have when we met at conferences. I'd open up the conversation by saying, my time step is so small, I'm sure your method must be better. And then he'd immediately counter by saying, yes, but the work done per time step in my code is so long that I'm sure your code is better. And I think they turn out to be about the same. I think in practice, if you actually look at his results, where he got down to in small, he was mainly dealing with plain parallel, actually. But the comparisons there, he seemed to be getting results quite similar to ours, and at about the same sort of resolution. So, although the methods are different, I don't think there was a huge difference in efficiency, computation efficiency.
Regarding the calculation of the time step, is the current condition?
Yeah, the current condition. The current condition is essential.
It depends on the motions.
Yeah.
Basically, that's right. I'm always a bit worried about that because I think the magnetic field can actually influence this.
Yeah, then it's the alveolar speed.
Yeah, it can, in fact, can also.
But it's
Well,
still,
so
it's still
that's,
proportionally
I mean,
meshed
yeah.
scale.
Some of the people that when we were sort of thinking about this, one of the ideas was to limit this the time step explicitly on the CFL condition. And I was always rather anti that because I thought that the magnetic field might alter that. So that's why I wanted to go for this dynamic directive.
So you actually estimate the time step based on the Adams-Weierstrass scheme?
Basically, that's right. Yes, the predicted corrector is going through.
So there's a difference between your n and n minus 1.
Well, you've got n. You've got n minus. You start on the predictor step. You have n and you have n minus 1. Yeah. Then you do the predictor step. Yeah. Then that gives you the field and the flow at n plus 1. You put that back into the nonlinear thing, so you get an improved estimate of the nonlinear thing actually at time t using the sort of partially incorrect but sort of approximately correct information at n plus 1, and you compare predictor and correction. You see whether the differences. You just look at the modulus of the differences, so to make so if anywhere is wrong, then you cut the time step.
Yes. Yes.
Yeah. Did anybody try to just to solve the nonlinear problem implicitly, like Newton-Klein or GMS technique?
Yes, that's what Stefan Stellmark did. Yes, I mean.
No, but that is finite difference.
Finite difference.
I was talking about your case.
Oh, in spectral. Oh no, that would be almost impossible, I think, because the actual variables are sort of in some sense almost lost by the time you actually go to the physical space and then back to the spectral space to try and sort all that out, to solve those equations implicitly at every time step. That would be just slow down. I mean, even in Stellmark's case, where he had a finite difference scheme, solving the equations was pretty time consuming at each step. That's what I said. I mean, he was doing a lot more work per step than we were doing. But he did get, of course, large time steps. So, I mean, because of the explicit nature of the calculation, that's limiting you in time steps. Yeah?
Some modelers use these hyperdiffusivities to damn small scales.
Yeah.
Can you comment on the usefulness of these approaches?
Well, yeah, that's a very interesting thing. I mean, I've done this myself too. I mean, I've done quite a bit on looking at that. The plus is that it does indeed damp the higher scales, so it enables you to get to a sort of a lower Ekman number, headline Ekman number, because, as I said before, the thing that's limiting you is the appearance of the small scales at the small Ekman number. So in some sense, it's a good idea, because it gets rid of small scale motions that we don't think are actually doing very much. However, there's a big however there. I mean, unfortunately, it appears that if you have slightly too much hyperdiffusion, the nature of the dynamo radically changes. Some of Glatzmeyer's early simulations had too much hyperdiffusion in, and if you look at his results, they look much more like alpha omega dynamos. The toroidal field is actually quite a bit stronger than the poloidal field. Those things that I was showing you there are much more like alpha squared dynamos. The poloidal field and the toroidal field are very comparable. So that the effect of the hyperdiffusion was actually changing the ratio of the poloidal and the toroidal components of the magnetic field. At that point, I got really worried about using hyperdiffusion because, I mean, now you're really changing. I mean, that's a really fundamental change of the whole dynamo process. I mean, if one model is producing alpha squared and the other is producing alpha omega type models, that really is worrying. And that's why I've sort of gone off hyperdiffusion, to be honest. I mean, maybe I got a bit paranoid after finding that out, and maybe there's still a role for small amounts of hyperdiffusion there, but it's got to be used with a great deal of skill and judgment if it's going to be used at all, because there is definite evidence out there that it can actually affect the nature of the dynamo process. And remember these tall, thin columns are actually crucial for actually producing this dynamo action. And they're fairly small-scale structures in themselves. Mess around with those, and you mess around with the whole dynamo process, and that's not a good idea.
So in essence, there isn't really much differential rotation.